So let's start the second presentation. Thank you again, Val, for such an inspiring presentation that you have. So today I'm going to speak about parallel blockchains. It's going to be more like of a high-level overview of how certain blockchains are trying to run transactions in parallel. First, a little bit about myself. I'm Vlad. I'm doing software development for the past 12 years. And for the last 3 to 4 years, I co-founded together with Marius and Iwan a company called QAD. Nice. Thank you.
You just need a bit of quantum computing.
And it's sorted out. We are doing Web3 and blockchain projects. One of our biggest clients is Sandbox.game. We started with 4 developers, and now we are over 20 developers in mainly in Timisoara, but all over the Romania. Now, so to give some context about why do we want to run certain transactions in parallel, let's go into the beginning. How many of you knows this picture or have? Okay, one, right. So this is how mainly blockchain started out. We had this issue of transferring some value from Alice to Bob. Let's say that that value is going to be like digital currency, $10 from Alice to Bob. And how we usually do this is using some kind of a centralized entity. In this example, can be a bank. Alice usually goes to the bank, authorizes some transactions, and then the bank does some black magic stuff. Usually it involves like centralized database, some centralized servers, maybe with some replications, but inside a private network. We don't really know what's happening there. We just know that after a couple of seconds, minutes, days, hours, the money arrives from Alice to Bob. Now, we've been doing this for the past 30 to 40 years. We are really good at doing this, especially in the last couple of years that the entire fintech industry like just blossomed. We know how to process hundreds of thousands, maybe transactions per second. It's really scalable. Now, what's the issue with this? Well, the issue is that maybe we don't really trust this centralized entity. Maybe something really happens with it and it just disappears, or they committed fraud. Something bad can happen. So this is how the actual blockchain and Bitcoin started out. There were some guys thinking, okay, how can we break this heavy centralization, and how can we see what's underneath this black box? So the first step is to decentralize the data. We are just having a bunch of nodes distributed in the entire world geographically, and we copy the state in every single node. How we interact with the system is like a general network. We want to initiate a transaction. That transaction goes to the system, usually goes somewhere in a mempool or sequencer, so on and so forth. And finally, it's going to end up in a node. That node is going to bundle this intent into a block, and those blocks are going to be distributed inside the network. Now, what's really important here to remember is that we are not distributing the entire state of the network or the entire data, but actually we are distributing operations on state, or in computer science, state transition. Now, blockchains can also refer as replicated state transitions because you are just replicating those state transitions across a distributed network. And to give you some idea, we maybe end up with hundreds of thousands of nodes. So scaling this system is really difficult. Right. As I mentioned before, so you can think of a blockchain as just some state transitions from state 1 to state 2. We are applying a set of operations, and those operations, we are chaining them. And this is having us, it allows us to have a nice property that if we want to see the state of the blockchain at a certain point in time, so for example, state 3, we just need to reply and to rerun every single operations that we have. Right, things are getting a little bit more complex and complicated because you don't just have numbers and decimals, like in the example of digital money, but we have random programs that are running. We have different data that can be changed. Like, for example, you can do minting, borrowing, bundling, exchanging, swapping, creating new smart contracts. So the entire state of the network is getting more and more complex. Now, if we go and try to analyze a little bit a transaction, which is a unit of work inside the blockchain, we can think about it in two main ways. First one is just a state transition from state A to state B. The second one is like a small program that takes some input data, does some operations, and then it spits out some output data. Right. Now, the hard part is to have this outputted data being distributed across the entire network. Ethereum mainnet does that with around 120 transactions per second. Usually, the centralized entities and the centralized databases are doing it with hundreds of thousands of transactions per second. So definitely, we need to reach a better scale in order to have what Val was just mentioning before. Now, one naive idea, which is really just one idea, is to bundle more transactions and to try to execute those in parallel. It's going to solve some problems, but not all issues, because you cannot bundle every single transactions. And I'm leaving out a lot of details in terms of consensus mechanisms, in terms of data transaction and data storage. I'm just going to focus on running those transactions in parallel. And maybe we're going to end up with a better number there. In the naive implementation, what we can do is just to try to bundle as many transactions as possible into one execution. Now, in the real world, as you may know, in any concurrency model, usually you cannot do that because you're going to have conflict data and certain transactions cannot be operated in the same time. In this example, like first transaction, the second transaction are depending on the same data that the third and the fourth transactions have. Now, in order to solve this issue, we need to be really careful on this state, what we mention as the state access, meaning how we access the data and how we make sure that the input data is always safe. In the blockchains that I analyze, there's two main schools of thoughts. And maybe you're going to see the same parallel as the classical computer science background. We have first the deterministic approach, and the second one, the optimistic approach. By deterministic, I mean trying to run the same set of transactions concurrently in different orders and having the same result in the end. And by optimistically, I just try to run those transactions and see what's happening. Now, for the deterministic parallelization, it's really difficult to do that if you don't know the data beforehand. So what all the blockchains are doing, they figure it out what the data what was the input data, and then they can sort the transactions and group the transactions so the data won't have any conflicts. We have the first example here, which is a really powerful name in the community, Solana. So Solana, a transaction in Solana looks like something like this. It's composed by a set of signatures and then a message. And inside the message, you have this small accounts array in which you have to declare beforehand what accounts, or in Solana, everything is an account, so everything that is data related needs to go there. This is adding a lot of overhead for the virtual machine and actually for the tooling itself, because as a developer, I need to know how to write the smart contracts in such way in which I need to declare those accounts. Now, Sergio knows a little bit more, but there is a lot of tooling that allows you to do that. And another side quest here is that you have to segregate the data and have a really complex data structure. In Solana, everything is an account. Like if I own some meme coin, that's an account. If I own some Sol, that's an account. But this is allowing us to do a lot of correlations between data. Now, as I mentioned before, inside the C-level or the Solana virtual machine, we know already what transactions are being executed and how we can then group those into multiple queues. And each queue has a sign of CPU core, meaning that we can run a lot of transactions in parallel, and it's going to scale by the number of CPU cores that we have on our validator. As a nice and interesting part, there is also this concept stolen from hardware design called pipelining, when you can pipeline the data. So we have different hardware components that are handling different operations in the transaction execution. So we have the CPU that can do multiple banking in the same time, and we have the GPU that can verify the signature of multiple transactions. So this is the result. We have here some nice theoretical number that is not achieved yet because we don't have this amount of traffic on Solana. Maybe those numbers are not really up to date. But the most important part is that the deterministic solution is one that kind of solves this issue. Now, on the second blockchain that we thought, how many of you knows about Sui? All right. Now, Sui, I spoke a little bit earlier in the beginning that in the blockchain you're going to have these state transitions, but Sui thinks a little bit differently on data access and data in general. So instead of having those state transitions in which you give Alice $10 and minus Alice gives Bob $10, you have an object-centric model in which every single piece of data is just an object that it's owned by somebody. And if you want to change the owner, then you just make one operation. So again, this allows us for a really simplistic way of thinking about data and really easy to find conflicting data inside the transaction. Because on Sui, things are getting a little bit more complicated when you have different ownership, different object can own different objects, and they are building a kind of DAG, decentric adjacent graph. And they can find conflicts really, really fast. Right, this is a max theoretical transaction per second from their experimental run. It's almost 300,000 requests per second. But I couldn't find like a really realistic play of it. But until now, it's like the most advanced and the fastest blockchain, I think, out there. Besides different blockchains that maybe they are doing different things like sharding that I won't discuss here. Right, one caveat, again, comparing it to Solana, is the virtual machine or the execution layer is on Move. So you have to know Move, another language, in order to write for Sui. OK, now for a really simple, some really simple example, we have the optimistic parallelization, in which, again, I mentioned that you just run a couple of transactions in parallel and then check for any conflicting or validation errors. There is this type of algorithms called optimistic concurrency control algorithms. It's a group of algorithms that are doing this execution in parallel and then just checking out. And the whole group of algorithms can be summarized something like this. You have multiple writes writing in the same data store. One of those that write is going to win. And the loser is just going to retry the execution. How we figure it out, which one is winning, which one is losing, and how to execute that is depending on certain algorithms. Now, one such network that is implementing this methodology is SEI. SEI, which is a network originally built on Cosmos, but they recently upgraded, and we have SEI v2, which adds an interop between Cosmos and EVM. In SEI, we have this execution engine, which is really basic. You have multiple execution phases and multiple interchain with some validation steps. So let's imagine that we run 3 transactions in parallel. The first 2 are going through without any issues. The third one fails because it has some conflicting data with one of those. Then it's going to be re-executed and revalidated again, and we are done. Now, this sort of pipeline works OK if you maybe have a small amount of transaction in the same block. But if you want to have more than that, it's going to end up really badly. So because we have this retrying mechanism and revalidating mechanism, we can see that the maximum theoretical TPS is really low comparing to the ones that are doing deterministic parallelization. But we can write Solidity, we can write in our lovely EVM manner. They did some optimization also at the state of database, which is really cool. They are running on top of RocksDB. OK, now maybe for the last and most interesting part is that in all this optimistic approach and optimistic research, we had a major breakthrough in 2022, I think. It was with block STM, which is a paper written by Aptos Labs. And inside this paper, you can see that they make a lot of parallel to the concurrency models that we have in classical computer science, meaning that they re-implemented software transactional memory, but inside blocks. That's the stands, like STM stands for software transactional memory. Software transactional memory is this holy grail of programming, of concurrent programming, in which you just write any concurrent programs that you want, and it's going to automatically solves any concurrency issue. Of course, it doesn't work really well in practice. And I don't know any programs or languages that are implemented this. I know that Python had a small experiment, but they failed. And how it works is that you need to trace each write and each read at the memory level. And if 2 variables have the same read and write, then one is going to roll back, and the other one is going to win. It's like having transactions inside databases. Now, Aptos was the first that implemented this. And their pipelining looks something like this. It's really similar to the SEI pipeline, meaning that you're going to have some execution and validation step all over again. The only difference or major difference is that you can run the execution and validation in the same time. But SEI is not doing this. It's just an implementation details. All right. So they also mentioned in the paper that you can do. They were doing this verification using multi-version data structure. What's a multi-version data structure? Well, it's just a way in which you can map inside the memory block the value of the variables and what was it when it was written. To make it easier, let's say that I have a variable A, and that variable A has a certain block of memory, and inside it, I mutate that memory with 52 for the transaction 1, and then for the transaction 2, I mutate it with 4, so on and so forth. And each time, I keep track of what I'm writing inside the variable. When transaction 5 came into pay, then it's going to read from a lower number than 5. So it's going to read from 2. But after that, everything after that is going to read from 6. It's kind of maybe harder to explain, but it's really intuitive if you just look at it. Right. With this approach, Aptos managed to pull over 100,000 transactions per second, which is a really impressive number. But we have a downside that they're also on move. So we cannot write in any Solidity, and all the major projects are already on Solidity. Now, for the last blockchain, Monad is not yet released, but they were thinking a little bit more over the entire architecture of their network, and they figured it out that actually you can execute more stuff async. What does it mean async? Well, a big part of a blockchain round, let's say, or the block time, is what is called in the terminology, is taken inside the consensus algorithm and in other pipelining stuff. For inside the Ethereum block time, you have 12 seconds block time, and the execution is just 120 milliseconds. Now, what you can do, so this is like a couple of rounds of execution. What you can do, it's actually shift a little bit. So once you figure it out what you want to execute, start executing, and right after that, start another consensus round. But this is actually translating in having more execution time. So you're going to have more execution time than 120 milliseconds, meaning that you can execute more stuff in the same time. They also implemented the same stuff that Aptos and Say implemented. And it looks something like this, but it's really more simplistic than the guys from Aptos. Again, you have the same number of executor as the number of CPU cores. You're going to have the transactions piled up, try to run, revalidate. As a small caveat, they also implemented the same thing as Solana, so meaning pipelining. So whenever you want to execute a transaction and you need the data, you can do a lot of stuff in parallel on different hardware, like signing and checking. You can do them on GPU. The rest you can do in CPU. And you can increase the throughput this way. Now, it's not that promising as Say, but again, take those numbers with a grain of salt because those are published by their team. They are using EVM, which is, again, an interesting thing. And as a conclusion, you can see here that most of EVM-compatible chains are doing really poorly in terms of performance. And the ones that are using deterministic approach are doing a little bit better than the one doing optimistics. Right, it was really short and condensed into everything, but thank you. And if you have a couple of questions, not more than that. That's it.